Auto PTR was actually deprecated. It was too powerful, meaning that it was doing too many things in a way that wasn't, we couldn't fine tune anything, and it was just like too over encompassing. But the ideas linger on, and it was actually split into three different smart pointers. First is called unique PTR. All three, by the way, are in the STL, the standard template library of C++. And you can actually create objects of these types. The first is called unique PTR. Unique PTR is exactly what I described as auto PTR, which means every memory must be shared by exactly one. You can't have two who are owning the same heap. You have the full transfer of ownership from one to the next. What I described as auto PTR is actually called today shared PTR. The next type of smart pointer that I want to discuss is called shared PTR. What is shared PTR? The idea behind shared PTR is the following, that every pointer, in a sense, besides the idea of using the destructor, is still a smart pointer, which means we're using the destructor to actually go and deallocate the memory, whatever, but it's done in a smarter way. What happens is that every object, in a sense, has a counter of how many pointers are pointing at it, which means it's like a reverse pointer. In a sense, besides pointing to whoever it's pointing, or whoever it is, there's a counter going on. So if we have, let's say, two guys pointing at the same location, so the counter here would be 0, here would be, let's say, also 0, but here would be 2. And the idea is that if two pointers point at the same location, then the location itself holds a counter which says, oh, I'm being pointed at by 2. Now, that will require that we again overload the operator, assignment operator, because the assignment operator, when you say A equals B, right? So in a sense, you have to increment what B was pointing at by 1, and decrement what A was pointing at by 1. Meaning if I had, for example, A pointing at some other location, wherever it was, I have no idea where it was, right? As it was pointing to some other location, and you write A equals B. So if this had 2 pointers at it, and this only had 1 at it, right? And then we wrote that A equals B, right? So now A does not point to here anymore. It points now to here. So this becomes 2, and this goes down to 1. So we had to overload the operator equals, overload the copy constructor, etc. But the idea is, it doesn't really make a difference how we're doing it, how it gets done. But the idea is that every memory would know how many pointers actually are pointing at it. Now, why is that important? When you leave scope, or you get deleted, or whatever, so we said that the destructor goes and it deletes the memory, reclaiming it, and then we can use it again. And we said that created a problem of dangling pointers, and we had to create a concept called transfer of ownership. The idea here in shared PTR is a bit different. The idea is, again, the destructor, when you leave scope or one gets deleted, the destructor will reclaim the memory. But it would only do it if the counter goes down to 0. Meaning that if the counter is now 1 and 1 gets deleted, so now the destructor would say, oh, it's going down to 0, let's reclaim the memory. So the destructor will look something of the code that looks something like, let's call it shared PTR. And again, I'm going to ignore the template. Right, it's a destructor, it's a shared PTR, right? And inside it would say if, let's say I'm just saying counter is equal to 1, which means it's my turn to delete it, or let's do it a bit differently. Let's do it first. Counter minus counter, and it would say if If counter is equal to 0, then delete the P. Else, don't delete the P. Now, notice what it's doing. It's decrementing. If 2 pointers are pointing at the same location, right, which is perfectly legal. So if we have 2 pointers pointing at the same location, here we have, right here. And it says over here, for example, it says 2. It says 2. And 1 gets deleted because it went out of scope. So then this will get deleted, this will get deleted, right? And this will go down to 1. But the actual memory itself won't get deleted. And then if the next one gets deleted and goes out of scope, then the destructor will go and say, oh, now it went down to 0. Now we get to delete the actual heap memory and reclaim it. And in that sense, by using shared PTRs, we are using, again, a smart pointer idea of not allowing for memory leaks. But in this case, we do not create the problem of dangling pointers at all. Because as long as anybody is pointing to that heap, or wherever it is, to that memory location, there's somebody there counting how many references to it there are. And by doing that, it doesn't get deleted, and we don't have a dangling pointer problem. Shared PTR, though, does have a problem. And let me discuss the problem. The idea is that we have a runtime stack. We have a runtime stack, and on the runtime stack, we have some pointer to the heap. Now, suppose that we have here the following picture. Somehow we got a circle, which could happen. If you have some kind of doubly linked list or some other whatever, you can easily create a circular reference. Now let's walk around and ask ourselves, what is the pointer counter, for each of these? So here 1 gets pointed, and here it's 1, here it's 1, but here we have a 2. There are actually 2 pointers pointing at it. Now let's think what would happen if the pointer over here on the runtime stack goes out of scope. So this will go down from 2 to 1. I hope everybody agrees. It goes down from 2 to 1. But none of this memory is reclaimed. Notice that all this memory is actually garbage. All this memory should have been reclaimed, but none of it is, because the destructors don't kick in. Every one of them has a counter of 1. And since every one of them has a counter of 1, then there's no reason why the destructor actually reclaim the memory. And notice what happens. So we have a circular referencing problem in this shared memory, shared PTR mechanism. If for some reason this happened, this wouldn't work. If it did not happen, suppose that we were holding here. So before we deleted the actual scope, and we had a picture like that, then everything will work. Because if the stack object goes out of scope, well, this becomes a 0, and this becomes a 0, and this becomes a 0, and that becomes a 0, and they all get reclaimed. But if for some reason we did have a circular logic, so all this wouldn't work because they would all have 1 in them. Every single one of them would have just a 1 in it. And since they all have a 1 inside, then none of them will get reclaimed. And we're actually having all of them being leaked. So notice that the shared PTR came to solve a specific problem, but it also has its own set of problems, right? The circular reference logic. Now, in order to solve this problem, created another type of pointer called weak PTR. Weak PTR, in a sense, is still a smart pointer, but it's still a shared pointer with one major difference. The difference is that it does not increment the pointer of what is being pointed at. Meaning that when you overload the equals operator, the assignment operator, or whatever it is, the copy constructor, or whatever you have to overload, what's actually going on is that it's not incrementing the pointers. And when it stops pointing at something, the pointers don't get decrement. So in a sense, if we had a weak PTR in this cycle, suppose the last guy here is a weak PTR, right? So even if this was all existing, the pointers will still be 1, 1, 1, 1, 1. We would not have a 2 up here, right? We would not up here, there's no 2 because these are weak PTRs. So you get to choose if you want to use a weak PTR or a shared PTR. And the difference between them is, do the pointers of what gets pointed at, do they increment and decrement when the pointer is added or removed? Now, if we had weak PTRs for this little problem, then we're in business. Why? Because if for some reason the stack pointer gets deleted, then this number goes down to 0, so does this, so does that, and they keep going down, 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 down. And once that happens, then all of them get reclaimed and everything's okay. But even though we have a circular logic and supposedly the number of pointers at this guy was originally 2, but only one of them was counted because this guy over here was a weak PTR, and only one of them was counted, and therefore we were able to solve part of the problem. Again, the bigger the problem becomes, when should you use a weak PTR, when should you use a shared PTR, when should you use a unique PTR? That's an interesting engineering question, whichever program is using has to decide when to use what. But in a sense, the idea was, let's take the smart pointers and split their usages in ways that we can actually afterwards go and say, oh, I want this, I want that. Much more fine tuning than the original auto PTR, which we had from the first minute. Now this is smart pointers, and this is actually in use today. It's actually within STL, Standard Template Library of C++. And as I said before, auto PTR itself is deprecated, it's not around anymore, but it gave the ideas behind a lot of what actually does function today. And it's not called, as I said, auto PTR, it's called unique PTR, but it's the same thing. You can actually use the transfer of ownership mechanism in your pointers. If you rather not, you can use the shared PTR. If you think that you might get into trouble with all kind of circular referencing, then you should think of using weak PTRs. But in a sense, the idea of using the destructor in order to reclaim the leaked memory, that's the basis behind what's going on in smart pointers of C++.